Hey guys, I'm Millard from CA Assistant. Welcome to this tutorial. In this course, which is the continuation of the Abaqus Introduction collection, as a first step, we're going to simulate an eye-shaped beam under different type of loads and boundary conditions to compare the result with the theory. At the end of this course, you will be well acquainted with the user interface and working with Abaqus. Before we get started, let's take a look at the training plan. In the previous section, I explained the training process to you. We also had a brief discussion on the finite element and Abaqus software. And finally got to know the software user interface. We said that the best method of training in Abaqus is problem-based. As I said, in this course we simulate a cantilever in a static and dynamic approach, then compare the result with the theoretical results. I suggest you see your next courses too. In the next course, we analyze the truss, then we work on simulation of composites. The next training package will be the simulation of metal forming process. This will be the first step of our training package. Next, we will learn thermal simulation and model analysis. But this is not the end of our training process. To see our teaching plan in this series of tutorials, check our website. Okay. As a beginner, you may not have any knowledge of software. We'll start with basic training. Where to start? What is the process of creating a software simulation project? You don't have to spend hours and be confused to figure out where to start. Abaqus software has a modular structure where in each of the modules we define some of the features of the problem. We will fully explain each of these modules, all the actions we need to define for the simulation in each of them. One issue we'll discuss in this example is the modeling method. In a beam simulation problem, the question that arises is what is the appropriate simulation method? 3D or 2D wire-shaped simulation? This issue will be thoroughly investigated and the differences expressed. Abaqus software offers a variety of solutions, such as static and dynamic solutions. In this tutorial, we will try to apply them to understand their differences. And last but not least, how to analyze the results. How can the result of the analysis be compared to the theory? Finally, we will discuss what variables and values will be obtained and how to work with them. You don't need to know anything to watch this tutorial, but it's better to watch the introductory tutorial before this. After watching this package, you can watch the next step, which will be about truss. This package includes more than 60 minutes of tutorial video. All the tips and steps will be recorded for you with high quality materials. It also contains 3 common and practical examples. And all the files of this package, all the examples files that describe, will be provided to you with video on our website. So, be sure to check out our website and our social networks to access all the training materials and download it and many other tutorial packages. Let's go to the main part. Before we begin to simulate, it may be better to review the theory of the beam. Beam is one of the most used structures in engineering field whose main task is to withstand the stresses caused by shear and bending anchors due to the loads on it and the weight of the beam itself. Beam has a very specific meaning in engineering mechanics. It is a component that is designed to support transverse loads, that is, loads that act perpendicular to the longitudinal axis of the beam. This is the main difference between the beam and the truss. The truss is designed to withstand only axial forces. The beam are used in bridges, transportation, aerospace, structures, and so on. Abaqus can simulate beams with different cross sections. The Abaqus beam cross section library contains solid sections and thin wall section, which include closed thin wall sections, open thin wall sections, and a thick wall pipe section. Abaqus also provides an arbitrary thin wall section definition. Abaqus will treat this section type as closed or open section, depending on how the section is defined. You can easily create your own standard or customized section in Abaqus. For more information, you can see the following link from Abaqus documentation. If the values of variables in third dimension are negligible, the simulation can perform in two-dimensional form by eliminating the third dimension values from the equations. The following elements can be used to simulate the beam in Abaqus: ordinal Bernoulli or slender beams, Timoshenko or shear flexible beams, linear, quadratic, and cubic interpolation formulations, warping or open section beams, pipe elements, and hybrid formulation beams. For Timoshenko and early Bernoulli beams, the references are in the assumption of both theories. In the ordinal Bernoulli, a cross-section is perpendicular to the Bernoulli line. In a Timoshenko beam, you allow a rotation between the cross-section and the bending line. This rotation comes from a shear deformation which is not included in the Bernoulli beam. Therefore, the Bernoulli beam is stiffer. However, if the rotation between length and thickness is large enough, the error between both models is small. You need the Timoshenko beam works for shorter beam structures. Beam elements use quadratic and cubic interpolation function, which makes them reasonably accurate for cases involving distributing loading along the beam. In the following training, I will talk more about this. When modeling beam in space, a further consideration arises from the possible warping of the beam's cross-section under torsional loading. For all but circular section, the beam's cross-section will deform out of its original plane when subject to torsion. This warping deformation will modify the shear strain distribution throughout the section. Two formulations are available for pipe elements in Abaqus. The thin-walled pipe formulation assumes constant hoop stress across the cross-section and neglects the radial stress, whereas thick-walled pipe allow the hoop and radial stress components to vary across the cross-section. Hybrid beam element types are provided in Abaqus for use in cases where it is numerically difficult to compute the axial and shear forces in the beam by the usual finite element displacement methods. See the links below for more information. Okay. I'll say where do we get access to these elements to change them during this training and later. But before that, in this section I was going to introduce you to Abaqus abilities to simulate beams briefly. As an Abaqus user, you need to know the theories to ensure that your simulation is correct and consistent. The best reference for information is the Abaqus documentation. It may not be bad to review some formulas before we begin to simulate. In this section, we will review the formulas for bending a beam for a few minutes. Then we talk about the problem and start the main part. And when we're done with the simulation, we compare the result with the finite elements method. From mechanics of material, we know that the deflection of cantilever is obtained from this relation, where P is load, L is beam length, E is Young modulus, and I is the moment of inertia of transformed section with respect to its centroidal axis. The formula itself is obtained as follows. The deformation of a member caused by the bending moment M is measured by the curvature of the natural surface. The curvature is defined as the reciprocal of radius of curvature ρ and can be obtained this equation. If you remember, this equation derives from submitting Hooke's law in the strain equation relative to the radius of curvature of the beam, which itself derives from geometrical relations. Also, recall from elementary calculus that the curvature of a plane curve at the point Q of the curve is considering the elastic state for a beam, and the simplification can be expressed as this. We may multiply both members of equations by EI and integrate in X. We write where C1 is a constant of integration, denoting by theta the angle measured in radians that the tangent to the elastic curve at Q forms with the horizontal, and recalling that this angle is very small, we have, by integrate in X again, we write where C2 is the second constant. The constants C1 and C2 are determined from the boundary conditions, or more precisely from the conditions imposed on the beam by its supports. Consider the cantilever beam AB with a uniform cross-section and carrying a load P at its free end. By submitting boundary conditions for equations, the deflection of beam obtained. Now, if the cross-section, load, boundary condition, or any other parameter changes, then we have to calculate the integrations again. You see how much calculation is needed to calculate a simple deflection of a beam. Notice that beams should be supported in such a way that the reactions at the supports can be obtained by the methods of statics. Otherwise, the problem will become more complicated. The same conditions exist for calculation stress. In summary, first you need to draw a free body diagram for the beam. Then you have to get all kinds of stresses such as bending, tensile and compressive and torsion stress, and so on. Then the result of normal and shear stresses for the critical regions of the beam should be calculated. After that, we deal with principal stresses and more circle. Finally, by submitting principal stress in criterion of material failures such as maximum shear stress criterion or Tresca, or the maximum distortion energy criterion or von Mises, we compare the stress with the yield stress of the material to see whether failure happens or not. You see how complicated this calculation can be? While by using the finite element method, in a much shorter time we can get the results. In addition, problems that are much more complex or even incalculable by manual method will be easily and quickly calculated from this method. Let's see how this can be done. We want to simulate the I-shaped beam under the concentrated transfer loading P. First, let's model it statically. Things that we need to solve for static include Young modulus, Poisson's ratio, and of course the amount of force and geometrical dimension. Let's consider the following values for the model. In these tutorials, we assume that the user does not know how to work with Abaqus. I already gave a full explanation in the Introduction to Abaqus overview video on finite elements, modules, and Abaqus fixtures. Be sure to watch that video as well. But I will try to briefly explain some things so you can join us from here if you haven't seen that video before. Okay, it's time to go to the cool part. When you run the software, Abaqus will ask you for a model database. You can create a model for finite elements analysis, or safety analysis, or electromagnetic model. Or you can open the previous model or run the written code. I am using Abaqus 6.14. In the newer version, there is no safety option. The last option connects you to the documentation if you have it installed, and at the bottom is a list of recent simulations which is empty as the first time. When you select a database, the home screen will look like this to you. Abaqus is divided into functional units called modules. Each module contains only those tools that are relevant to a specific portion of the modeling task. The appearance of the window changes as you work through the modeling process by moving between modules. So you are being guided toward completing the model on consecutive windows where you're user-friendly, and in each window you define a bunch of problem features and work on one aspect of your model. These classifications are done in such a way that they can be repeated for each simulation problem. This is a great feature of Abaqus. The module list is in here in context bar. Other items in the context bar are a function of module you are working in. For example, the context bar allows you to retrieve an existing part while creating the geometry of the model, or to change the output database associated with the current viewport. We will return to modules later, but before that I want to illustrate the components that appear in the main window. Like most of the problem, there is a menu bar that contains all the available menus. Different menus appears in the menu bar depending on which module you are selected from context bar. At the bottom of the menu bar is a toolbar which provides quick access items that are also available in the menus, but they are useful and you can customize your favorite tools. The model tree provides you with a graphical overview of your model and the objects that contain such as parts, materials, steps, loads, and output requests. The model tree provides a convenient, centralized tools for moving between modules and for managing objects. If your model database contains more than one model, you can use the model tree to move between models. When you become familiar with the model tree, you will find that you can quickly perform most of the actions that are found in the main menu bar, the module toolboxes, and various managers. The second tab of this field is Result Tree, which provides you with a graphical overview of your output database and other season-specific data such as XY plots. In fact, in this section, the model tree of the pre-process and post-process are separated. Try learning to work with the design tree because it speeds up a lot. Here is the toolbox area. When you enter a module, the toolbox area displays tools in this toolbox that are appropriate for the module. Most of the features are shared in the toolbox and menu bar and design tree and are accessible from all these three locations. The canvas can be thought as an infinity screen or bulletin board on which you post viewports, and viewports are windows on the canvas in which Abaqus displays your model. The prompt area, which is here, displays instructions for you to follow during procedure. For example, it asks you to fill the part dialog to create the part or sketch section for extrusions. Abaqus prints status information and warning in the message area, like the creating model database we did moments ago. The message area is displayed by default, but it uses the same space occupied by the command line interface. You must click in the bottom left corner of the main window to change between them. You can use command line interface to type Python command and evaluate mathematical expressions using the Python interpreter that is built into Abaqus. The interface includes primary and secondary prompts to indicate when you must indent commands to comply with Python syntax. Well, the only things left is the mouse keys actions. You can use standard Abaqus mouse action for Abaqus manipulation. These actions are available from this menu, but I strongly recommend Catia's mouse actions. If you have worked with Catia like me, you would prefer not to get used to the new option. And the good things about these actions is that actions can only be done with the mouse, and you don't have to use keyboard, that I think is very good and speeds up. You can also use the view manipulation toolbar, which is here, and the view toolbar can be useful too. I'll explain this action later because we need a part to work with these actions. So now we want to create the model. Look, we have these modules to simulate. The part module is for creating individual parts by sketching or importing their geometry. Property module is for creating section and material definitions and assign them to the regions of parts. Assembly module is for creating and assembling part instances. The point is that even if you have one part and no assembly, you need to import it into this module to change the coordinate system from local to global. The first three modules illustrate the physical and mechanical properties of the simulation problem. In the step module, we create and define the analysis step and associated output request. Actually, you define the solution method, such as dynamic or static or modal or heat transfer or any other method, and loading and unloading process. Suppose we want to simulate a deep drawing process such that sheet holder grabs the sheet in the first step, and in the next step the punch move and pull the sheet toward the matrix. These steps need to be creating for this loading procedure. Interaction specify interactions such as contact between regions of a model. The assembly we did in the previous module determined the position of the components relative to each other in space. In this section, we determined the physics of these components relative to each other. For example, the two surfaces that are overlapped are frictionless, have friction, or have no contact at all. Load is for specifying loads, boundary conditions, and fields. In mesh, we create a finite element mesh, and optimization creates and configures an optimization task. These modules were intended to simulate or define the pre-process of the problem. Look, Abaqus is an application based on finite elements codes, with pre-written theories and different types of elements. The core of the software is these solver codes, but working with code for the user can be frustrating and difficult. That's why a graphical interface was designed to write part of this code with each user function. This is called a graphical user interface, or GUI, which we are working on it right now. The job module is for submitting a job for analysis or monitor its progress. In fact, by doing that, we give the code that was written to the solver to compute the equations. This step is called processing. After the processing, it's time to examine the results of the calculations. This is called post-processing. Visualization module view analysis result and selected model data. It actually helps us to see numerical results physically in stress contours, colors, and deformed shape. Sketch create two-dimensional sketch. This module is actually previous step of the part module, which is also available from the part module. Well, now we want to make a part. There are three ways. Double click on the part from the design tree. From toolbox, click on create part. From the part menu, click on create. All three do the same things, and by clicking on each one, the create part dialog box appears. I name it beam. You can define a part to be either 3-dimensional, 2-dimensional, or axisymmetric in Abaqus model. Abaqus carries a part modeling space through the modeling process. For example, modeling space determines which tools are available in the part module and which elements are available in the mesh module. In fact, by selecting it, you specify the properties of the problem and the premise. As you know, all problems are 3-dimensional and there are no 2-dimensional phenomena in the world around us. But under certain conditions, for states of stress and strain, solid problem can be converted to 2-dimensional by simplifying. Plane stress and plane strain problems are good examples of this. For example, on thin and constant thickness plates, which thickness is less than 1/10 relative to other dimension, if loading on the same xy plane takes place, it is an plane stress. Or if the thickness of the part is high and the cross-section area is uniform and part length is long, by applying loads along with the thickness, the problem is a plane strain. When geometry and loading have symmetry around the central axis, the problem is axial symmetry. The existence of both conditions is required simultaneously, and the lack of geometric or loading conditions makes the problem non-axisymmetric. Cylindrical, conical, and spherical vessels under internal or external pressures and many pressure vessels are axisymmetric problems. And you can also define a part to be either deformable, rigid, or Eulerian. The deformable is for the part where the strain is caused by the load and stress, while the rigid part is not deformed. I will explain the differences between discrete and analytical later in the examples. About Eulerian, as you know, there are two perspectives in mechanics. The Lagrangian, which is mass control, is the basic of solid mechanics, and Eulerian, which is a volume control, and it's used more in fluid mechanics. The point is that in the mechanics of solids, sometimes using volume control can help a lot. For example, in cases with very high deformation and of course in fluid problems. And the base feature field is to define shape and type of new parts base feature. The shape and the type options that Abaqus displays depend on the parts modeling space and type. If you have a sheet that is thin and the values of variables are negligible in the third dimension, you can model it as a surface to reduce the computation. The type field is the method of modeling geometry, exactly similar to modeling software like SolidWorks, CATIA, Inventor, and others. The last option is approximate size. These options specify the two-dimensional sketch plane size. This value must be 5 or 6 times the size of largest sketch dimension to fit inside it. Alright, since it's time to enter a value for length, there is one more important thing to say now. In Abaqus, values have no units. The user must enter values in the desired units. This is a very important issue. If you enter values in the SI, you get the result in the SI, and you have to make sure that all the values are in the SI unit. In fact, the unit of results is based on the unit of values you enter. If you would like to know more about this, go to our website. There is an article with this subject that can help. This table also shows the unit that can help. We are currently using these units. Well, we want to create a 3D beam, deformable, solid, with extrusion. For extrusion, we have to draw the cross section of the I-shaped beam. The largest size is about 2/10 of a meter. So I enter 5 times more means 1 meter for the approximate size. The one that we entered for approximate sizes was for defining this plane size. This blue grid is 1:1. It actually has no effect on the solution. Try to enter a decent amount of your problem dimensions. Well, let's draw a cross section of the beam. There are various tools for drawing such as rectangular, circle, oval, arc, and so on. Some tools have a small triangle at the bottom. Left click and hold to show the rest of its tools. Well, you can click on the screen to select a point. The point where the mouse is located display at the top left on the screen. You can also enter the coordinates in the prompt. Well, I enter 0 for x, comma, and 0 for y respectively. I don't know if you work with CAD software, but it's better to draw roughly than finalize by adding concentrates and dimension to it. So I try to draw an I shape by choosing a few inaccurate points. Okay, first fix the starting point. By using constraint and equal length, make these lines equal. To select lines as written in prompt area, hold Shift key and click on lines and click on done. You can use the mouse as scroll button instead of done. When dimension and constraints are fully defined, the color turns green. Well, there are many tools in the Sketch and Part module. Explaining all of them is time consuming and greatly enhance the time of this training, but you will need it for your future work. So in addition to the tutorials that come with the different examples, we are working on a series of tutorials that explain all the tools and options of some of the module inside. This means that each tutorial is dedicated to the tools of a module. Well, now our part is ready. Now let's take a look at the design tree. First of all, in front of the model, inside the brackets, it's written 1. We can have more than one model with different properties in the modules. This feature is very useful when you want to make a copy of a project and make changes to the step or part, for example, and keep the previous model. This model includes the part, property, step, and other modules and other specifications. If I expand part, we have a part. This is a beam part we created right now. You can copy or edit this file by left click on it. In the edit window, the options we had when creating the model are available. For example, you can change the model from deformable to rigid. The features used are also editable. These things are available here in Part Manager too. These manager tools are next to many Abaqus tools. It can edit what we have defined with its tools. Okay, we created our part in this simulation. Well, let's go to the property module. You can see that with the changing of the module, the toolbox has changed too. And you can see managers of these tools in this module. Here we want to determine the mechanical properties of the material of the beam. To do this, we must first define a material mechanical properties. In Abaqus, there is no material bank with all the properties. Instead, you need to specify the properties of the material for the software. This is done with this tool. Before we create the material, let's talk about the most key actions. All the actions can be done with the view manipulation tools, like pan, rotating view, magnify view, and others. MB is mouse button, so you can pan view with holding mouse button 2. Rotate view with click and hold mouse button 2 and mouse button 3. For magnifying, hold the second mouse button and click on the third mouse button. The rest of tools and view tools can help too. Okay, let's go back to the property module. Material definition specifies all the property data relevant to the material. You specify a material definition by including a set of material behaviors, and you supply a property data with each material behavior you include. You use the material editor to specify all the information that defines each material. Each material that you create is assigned its own name and is independent of any particular section. You can refer to a single material in as many sections as necessary. Abaqus assigns the properties of a material to a region of a part when you assign a section referring to that material to the region. You can use the Edit Material dialog box to create new material or edit existing material. When you select Create Material, you can enter the name of your choice for the material or accept the default name. You can provide a description for the material. Many dialog boxes have this description field. Many times, the number of analyses increases and the project gets longer, and when you return to the project after some time, you don't remember which model the properties belong to. Writing a description is very helpful for this. All the properties you can define for the software are grouped here into 5 categories. But they are not limited to these, and you can write your customized behavior. For example, suppose we want to define elastic behavior for a material. Well, the first option is a linear elastic behavior. Linear elasticity is the simplest form of elasticity available in Abaqus. Next is hyperelastic options, most commonly used for rubber and polymers, which is divided into isotropic and anisotropic. The anisotropic hyperelastic model provides a modeling capability for materials that exhibit highly anisotropic and nonlinear elastic behavior, such as biomedical, soft tissues, and fiber-reinforced elastomers. The isotropic hyperelastic model describes the behavior of nearly incompressible materials that exhibit instantaneous elastic response up to large strains. You can also create a hyperform material model to describe a cellular solid whose porosity permits very large volumetric changes. You can create a material model to describe a low-density, highly compressible elastomeric foam with significant rate-sensitive behavior, such as polyurethane foam. You can create a hyperelastic material definition to describe a nonlinear small strain elastic material. A porous elastic material model defines the elastic parameters for a porous material. You can define viscoelastic behavior in a material as a function of frequency for steady state and small vibration analysis, or as a function of reduced time for time-dependent analysis. If the properties of your material were not definable by any of these, you can define the properties by writing the mathematical relation that the material follows, and define it with a subroutine to replace it into solver codes instead of regular standard codes. Also, different models of plasticity, types of damage models for different types of materials, and other options can be defined. Other properties such as thermal, electrical, magnetic properties, as well as subroutines and density from the general menu, and a number of other properties from this tab can be defined. You have to define the properties based on what analysis you want to do. You see, in this section I explained just about elastic properties. To see a lot of properties can be defined for a material, and it's a power of the Abaqus software that can simulate the most up-to-date and complex issues. If you want to know more about any of these, the best source is software documentation. You can find out more by following the link below. A simple way is to click on this option and click on the point in which you want to know more about it. We want only linear elastic for this example. Any features you add will be added to this list. The elastic material can be isotropic, orthotropic, or otherwise. That means properties in different directions have different behavior. For now, in our model, the behavior of material in all directions is the same, which is isotropic. The elastic material can be isotropic or orthotropic or otherwise. That means properties in different directions have different behavior. For now, in our model, the behavior of material in all directions is the same, which is isotropic. If your material includes temperature dependence, you can enter data to define how material properties vary with increase in temperature. This number of field variable option is similar to the temperature dependent data, except that you can write a subroutine for any arbitrary variable whose properties are dependent, such as temperature like previous. You can tick the no tension or no compression option if your material is not tensile or pressure resistant, such as concrete that is not tensile resistant. In this example, we do not need any specific changes to the setting, and all the settings are OK by default. Well, we entered 210 E9 for Young's modulus and 3/10 for the Poisson's ratio. E9 means multiplying 10 by 9. To specify for Abaqus this material belongs to this part or region, we need to create a section. You may have several parts that each part have a different material. To do this, you will need to create a section. Sections are not just for assigning a material to a part. In beam sections or shell sections, we actually specify the properties of the elements and the properties of the cross-section of profile. But now we just want to make a section of homogeneous material full of solid with the still properties that we defined. Click to assign a section to assign. At prompt area, Abaqus asks to select regions to assign section. I click on the part and click on Done button. I select the previous section and click OK. Abaqus colors the region green in the property module to indicate that the region has a section assignment, or color the region yellow if there are overlapping section assignments. If you deleted section used in a section assignment, Abaqus colors the region red to indicate that the section is not found. This method of material allocation in Abaqus allows you to assign different material to different regions of a part. Suppose this beam has a material from tip of the beam to the middle and another material for the rest of it. You can easily assign these materials by partitioning it with which I will say later. Well, a lot of things can be done in the properties module, such as defining composites, beam section, and more. But for this simulation, we are done with this module. So far, we have created a model of beam and defined its properties. In the assembly module, we worked with instances. A part instance can be thought of as a representation of the original part. You create a part in the part module and define its properties in the property module. However, when you assemble the model using the assembly module, you work only with instances of the part, not the part itself. You create part instances in the assembly module. You then position those instances relative to each other in the global coordinate system to form the assembly. You can create and position multiple instances of a single part. So, a model can contain many parts. However, it can contain only one assembly. The assembly is composed of instances of the part positioned relative to each other in a global coordinate system. When you create a part instance, a list of model parts will be shown to you. We only had a beam part. If we had another part, it was here. You can choose to create either a dependent part instance or an independent part instance. You can also edit a part instance and change it from dependent to independent or vice versa. When you create a model instance, it is always dependent. By default, Abaqus creates the dependent instance of a part. A dependent instance is only a pointer to the original part. In effect, a dependent instance shares the geometry and the mesh of the original part. As a result, you can mesh the original part, but you cannot mesh a dependent instance. When you mesh the original part, Abaqus applies the same mesh to all dependent instances of the part. In contrast, an independent part instance is a copy of geometry of the original part. You cannot mesh a part from which you create an independent part instance. However, you can mesh the independent instance. In addition to meshing, you can perform most other operations on an independent instance. For example, you can add partitions and create virtual topology. The disadvantage of independent instances are that they consume more memory resources, and you must mesh each independent instance individually. In our example, since we have only one instance in the assembly, the dependent and independent are no different. One option in this dialog box is auto offset. I click on the beam in the list, then I click on apply. If I click on the beam again, because in the assembly the local coordinate origin center of part located on the global coordinate origin of assembly, the new part is placed in the same place as the previous part. Selecting this option will automatically offset the new instance. The rest of fixture in this module are very simple, includes linear pattern and radial pattern. Again, we'll talk more about that in the next few examples. Okay, in the step module, we want to define the solution method. Within a model, you define a sequence of one or more analysis steps. This step sequence provides a convenient way to capture changes in the loading and boundary conditions of the model. Changes in the way part of the model interact with each other, the removal or adding of parts, and any other changes that may occur in the modeling during the course of the analysis. In addition, steps allow you to change the analysis procedure, the data output, and various controls. You can also use the steps to define linear perturbation analysis about nonlinear base states. You can use the replace function to change the analysis procedure of an existing step. You can create a step by clicking on its button on the toolbox area. The Create Step dialog box appears. If desired, use the name text field to change the name of the new step. The initial step allows you to define boundary conditions, predefined fields, and interactions that are applicable at the very beginning of the analysis. For example, if a boundary condition or interaction is applied throughout the analysis, it is usually convenient to apply such conditions in the initial step. Likewise, when the first analysis step is a linear perturbation step, conditions applied in the initial step form part of the base state for the perturbation. The initial steps is followed by one or more analysis steps. Each analysis step is associated with a specific procedure that defines the type of analysis to be performed during the step, such as static stress analysis or transient heat transfer analysis. You can change the analysis procedure from step to step in any meaningful way, so you have great flexibility in performing analysis. Since the state of the model, such as stresses, strains, temperatures, and so on, is updated throughout all general analysis steps, the effect of the previous history are always included in the response for each new analysis steps. There is no limit to the number of analysis steps you can define, but there are restrictions on the step sequence. You can create any sequence of procedures that are allowed by the Abaqus analysis products. The procedure list in the Create Step dialog box is updated to show only the available procedure for the new step. For example, if your first step contains a static stress displacement procedure, you cannot follow it with a new step containing a heat transfer procedure. Or if you create a frequency analysis with the first 10 modes, these options are added. I remove the previous step and add a new static general step. In the description, you can add your information. Time has no effect on static analysis, but we need it for another purpose, so we don't change it. NLGeom is to indicating to account for geometric nonlinearity or not, and automatic stabilization is for defining the damping factor. We will talk about other settings on this page later. Let's go to the incrementation tab. There are three concepts about time in Abaqus: step time, increment, and time frame. The step time is the time required for that step. The summation of the time steps is equal to the total time of the solution. The increment is a fraction of the step time, and step time is divided into it. At the end of each increment, the results are available for writing to the output database. The increments at which you select result to be written to the output database file are called frames. In the maximum number of increments field, enter the upper limit to the number of increments in the step. The analysis stops if this maximum is exceeded before Abaqus arrives at the complete solution for the step. Automatic makes it possible for Abaqus to take the appropriate step increment according to the solving algorithms. In the initial field, enter the initial time increment. Abaqus modifies this value as required throughout the step. In the minimum field, enter the minimum time increment allowed. If Abaqus needs a smaller time increment than this value, it terminates the analysis. In the maximum field, enter the maximum time increment allowed. You can also read more about this subject here. In this example, these items do not need to be changed. In the step module, another important task we do is to determine the outputs in field output and history output. Abaqus has selected a number of outputs by default for any analysis, so we have nothing to do with it. Since we have no contact between parts in this example, we don't need to do anything in the interaction module. In the load module, I first create a boundary condition, a displacement rotation.